Hello everyone. So in this video, we are going to discuss that how we can use one online simulator for simulation of any Verilog HDL code. So before going to that simulator specification, so first I shall discuss a few lines regarding Verilog. Okay. So Verilog is a programming language. So it is one type of HDL, that is HDL stands for hardware description language. Okay, so there are two types of hardware description languages are available. Okay, so one is Verilog, another one is VHDL. Okay, so both are hardware description language. Now the advantage of using hardware description language is so you can efficiently and easily describe any digital system with the help of those programming languages. Okay, that means suppose you are going to design one arithmetic logic unit, or you are going to design any digital system. If you know the logic of that digital system, you can easily implement it with the help of those programming languages. Okay, and most important thing is that so there is a design portability. So design portability means so if you write a program in a Verilog or VHDL, so that is supported across all simulator. That means suppose one company, okay, is having its own simulator, okay, for this digital design. So another one company that is having it's a different type of simulator, but all simulator, okay, follows that same coding style, that is same type of language. That means the same code you can run in a different platform. Okay, and that may be any Windows platform, a Linux platform, or maybe for different simulators. So the design portability exists. So no need to change your code. Okay, you might have to change the project settings, but no need to change the code. Okay. So another one major advantage of this Verilog or VHDL is after writing this code and after synthesizing this code, okay, you can generate an object file or object code, okay, that is called bit code. Okay, and inside that bit code, all information regarding the hardware is stored in a binary format, and that bit code can be downloaded in a programmable hardware called FPGA. Okay, that is called FPGA. Okay, field programmable gate array. Okay, so it is one type of programmable hardware similar to your microcontroller. Those who are working with Arduino or any Atmega board, you know it's a programmable device. So you can write a C program and you can download that. Okay, the same thing, the approach is same. So here you have to write the program in Verilog or VHDL, and ultimately you have to generate one bit code, okay, the object code, which is a binary file, and that binary file can be downloaded, can be dumped into the FPGA hardware. Okay, and then the whatever the logic, okay, you are trying to implement, the code you have written, okay, the same logic will be implemented inside FPGA. Okay, so this is one of the easy method to implement or to design any projects. Okay, so without spending much time. Okay, so just you need one programmable hardware that is called FPGA, and that software required to compile, to synthesize the code. Okay. So in our lab, we shall use the Verilog, not VHDL. Okay, so the purpose is the same. So that the coding is different. VHDL is one type of language, Verilog is another one type of language. Both are hardware description language. So we are going to use the Verilog. Okay. So now in Verilog, okay, suppose the first program we are going to implement is a full adder. Okay. Now you know for a full adder, the logic diagram looks like this. So the logic diagram I'm drawing, you can check that. Okay. So this is basically sum. So if the input is A, this is B, this is CI, carry input. Okay. So output will be sum S. Okay. So sum basically XOR operation of A, B, and CI. Okay. And what about carry part? The carry part, you know, that is basically, okay, I'm drawing it in the next page. The carry part basically, you can say that is the 3 AND operation will come, said that is A, B, that is B and CI, and this is A and CI. Okay, and finally one OR gate will be connected. So this is C0. So this is the carry part. Okay. So sum part, that is the OR operation of ABCI. The carry part, that is AB or BC or CA. Okay, so that means AB, BC, CA, and the output of 3 OR AND gate is finally OR to get the expression of C0. You are already familiar with that. Okay. So how we can implement this system, that is a single bit full adder, okay, in a Verilog. Now in Verilog, there are different types of logic design style. That means you can write the code of any digital system using different technique or different modeling style. Okay, the first basic level is called the gate level modeling. Okay, the first basic level modeling is gate level modeling. The gate level modeling, you need to know the exact Boolean diagram of the logic you are going to implement. So without the logic diagram, you cannot implement the gate level circuits. Okay, that means to write the code, you need to know the Boolean diagram or the exact logical diagram of the system. Okay. Second type of modeling style, that is called data flow. In data flow modeling, no need to know the diagram of your digital system, but instead of diagram, you need the Boolean expression or the relation between input and output. Okay, so here diagram is not important, but Boolean expression is important. Okay, so for example, suppose in the previous case, the full adder, the sum is, we got the sum equal to S equal to what? A XOR operation of B, XOR operation of CI. Okay, that is the sum. And C0 carry, okay, C0 equal to how much? AB, A dot B, or operation of B and CI, or operation of A and CI. There might be some different expression of C0 also. Okay, after simplification, you might get some other expression also. Okay. So this is the expression for C0. So for data flow modeling, you need this expression and this expression. But what is the exact shape of the diagram? What is the internal connection? That is not important. Okay. So initially, we shall study these two type of modeling, that is gate level and data flow modeling, and some other types of modeling will come for a complex system. That means where it is difficult to get one Boolean expression between input and output. Suppose you have a 5 input, 10 input, a digital system. Okay, so it's very difficult to get one relation, Boolean expression between the input and output, or it is not possible to get the diagram of the system. Okay, because our target is to design a complex system, not a simple one. Okay, for simple system, the dedicated IC chips are available. Suppose you are talking about full adder, the full adder IC is already available. Okay. So for that case, you have to go to the other type of modeling style. Okay. So those will come one by one. So another one attractive feature of this Verilog programming or the HDL programming, basically, suppose you design a single bit full adder. The same design you can reuse, okay, for your next step. That means basically it follow the hierarchical approach. So design hierarchy is present. That means suppose you are going to design a 4-bit full adder. So implement a 4-bit full adder. To construct a 4-bit full adder, you need a 4 single bit adder. You know that thing. To design a 4-bit full adder, suppose you want to add 2 4-bit number. Okay. So for that you need 4 single bit adder. Okay. So you have already designed the single bit adder. So no need to write the code for single bit adder again. So you can just call that single bit adder function, that is called module. In Verilog, we shall use the term module, not function. Okay. So you can call the module of the single bit adder and then just connect in a particular way. Okay, so that the 4-bit adder will be designed. Okay. So basically, this programming language support a design portability. Apart from that, some other features are also there. So we shall discuss those things one by one when it is required. Okay. Now let's come to the simulator. So how we can design it. So we shall start with the get level modeling first. Okay. Then we shall go to the data flow modeling. Okay. So let's come to the simulator. The simulator it is an online simulator, so you can just type EDAplayground.com here. Okay, make sure that that Java is enabled in your machine, because sometimes it may create a problem if Java runtime is not running properly. Okay, so EDAplayground.com, and initially, so I've already logged in. Initially, you have to create an account. Okay, so I have already created the account. Okay, so there are so many options will come. So you can log in using your social network, and that is already the methods are already circulated through your PDF. Okay. The PDF documents you can check, which is already circulated. Okay. So just create a free account using your social network. Facebook login is there. You can log in through a Google account, Facebook, whatever. Okay, that is. So ultimately, you will get this type of platform. Okay. Now, there are two windows. See, there are two windows. One is design window, design.sp. Another one is test bench window, test bench.sp. So let me tell you what is design window. So design window means here you have to write the code, the main code that you are going to design. Suppose a 1-bit full adder. Okay, so you have to write the code for 1-bit full adder using any particular modeling style. Okay. And a test bench, the purpose of this window is to test your design, whether your design is working properly or not. Suppose you have already coded the design, okay, and it is running, but whether you are getting proper output or not. That means in a digital system, generally we put the input in the digital form. You know how to verify any digital, suppose a logic gate, how to verify that by checking its truth table 0001, 1011, etc. So in a test bench window, we shall do the same thing. We shall apply some standard test input, okay, and we shall check the output in terms of waveform. Okay, after simulation waveform will come, we shall check the output in terms of waveform. Now check for a different input whether you are getting a correct output or not. So the function of test bench is to test your design. Okay, function of design here, your actual digital system will be implemented here in the design, but in test bench, so you are going to test your design. Okay. So how to write a design code? Okay. So since it is a new language, okay, new programming language, so you need to be careful, okay, while writing the code. Okay. Suppose you got a single bit full adder, so all Verilog program, whether it is a adder, subtractor, or any Verilog program, whenever you are writing code, it starts with the thing module. Okay, you have to write a module. Okay, then give one module name. Suppose I gave a full adder. Now remember, when you are giving the module name, so do not start module name with a number. Suppose you are writing 1 full adder, 2 full adder, do not give that. Okay, so always starts with some character, means not number. Okay, so full adder, and there will be no space between this. It should be continuous. You can put number after this, means after this first digit you can put a number, but it should not start with a number here. Okay, and it should be continuous. There will be no space. So if we write full space adder, that is wrong. Okay, so you can give this full underscore adder, that is okay. Okay, then within this bracket you have to write what are the input and output of a full adder. Okay, now from our previous discussion we know that for a single bit full adder there are 3 input, A, B and carry input, and 2 output is there, sum and carry out. Okay, so please make one practice. You can write it randomly, that is not a problem, but I suggest you to follow the uniform pattern. That means always mention output first. So output means here sum C0, okay, is the output. Okay, and A, B, Ci is the input. Okay, so here I am writing CO. Well, you can write C0, no issue. Okay. So module full adder, first write the output term, SCO, then input term. Okay, so please make this and follow this throughout your Verilog programming. Okay, then semicolon. Then the next line you define your input output here, because here in the module, so this line indicates you are going to implement a digital system of module named full adder. Okay, and whose ports are SC0, ABC, but the simulator don't know which one is input and which one is output port. Then you mention which one is input and which one is output. So here no need to follow the sequence. Okay, so that means here I can write input A, comma B, comma Ci, output S, comma CO, or you can write output first then input here. Okay, so that is not important, but here, so always follow the sequence inside the module. Okay, also you can write the same thing, input A, semicolon, in the next line input B. Okay, similar to any other programming languages. Okay, so that is basically port declaration. That means now we define a system. The module name is full adder, which is having 3 input A, B, Ci, and 2 output S and C0. Okay, then you have to write the logic. That means, see here you just mention the module name, but how the module will be implemented, how the system will work, you have to write the digital logic. Suppose I am going for a get level modeling, so this is a comment line, get level modeling. Okay, this is a comment line. Now here then you write, suppose get level modeling means we are going to design the circuit using the logical diagram. You know the sum expression, okay, basically A, XOR operation of B, XOR operation of C. Okay, so we need one XOR gate. Okay, give one label name of the XOR gate. Whenever you are using any logic gate, always give one label name. Okay, now in the XOR gate, always mention the output first. So that is the standard format. Okay, this XOR gate, this gate is already stored in the library when you are calling a XOR gate. Okay, and when you are giving the parameter inside this, okay, so it will calculate the XOR operation. So output is sum, input is A, B, Ci. So that is basically inside S, the XOR operation of A, B, Ci will be calculated. We are calling one XOR gate. Label is L1. You can give any user defined name here. Okay, but the label name should be unique. Means in the next line, if you are going to use another one logic gate, you have to give a different label name. The next one is, the carry equal to AB plus BC plus CA. So we need AND gate and OR gate. So AND gate, let's give one label L2. Okay. So let this AND operation will be similarly, first one is output AB. Okay. That means the A and B, this result will be stored inside W1. Here I have not defined or declared W1. What is W1? I will declare after this. Okay. Similarly, in the next AND gate and L3, take another one temporary variable. So it will store B, AB, BCI and L4. Another one temporary W3, A, comma, CI. Okay. Now see, the meaning of this line, the AND operation of A and B will be stored inside W1, and operation of B and CI will be stored inside W2, and operation of A and CI will be stored inside W3. Now finally, Cout will be OR operation of this, that is AB plus BCI plus ACI. So we are calling one OR gate, give one label name, okay, L5. So output will be CO. Okay, what is the input? W1, W2, W3. Okay, our programming done. So write this at the last one, end module. Now we have to define W1, W2, W3. So W1, W2, and W3, those are basically temporary connections, or it is defined as wire in Verilog. So wire W1, W2, W3. Okay. So this is done. After writing this code, okay, since it is a online simulator, so if there is any problem in network connection or something, okay, so the code may be lost. So I suggest you to take a backup of this code, copy this code and store it in a notepad. Okay, so do not paste it in a Microsoft Word. The format will be changed. Okay, you can simply open notepad and okay, take a backup of this code. Fine. Now at this stage you can run this, but you will not get any output because the test bench is not mentioned. Okay. So let's see whether any syntax error is present or not. Okay, we can check it. Now the left side, let's select the simulator. In the select option, you select ALDEC, okay, Revira Pro. Okay, this simulator. Okay, no need to change this one. Runtime by default it is 10 milliseconds. No need to change it. Okay, if required, we can change it later. Okay, and since we are not writing test bench, so we'll not get the output. Okay, but whether any error is there or not, you can check it. Okay, so I'm running this, taking one backup. Yeah, so there is no error. Okay, till now there is no error. Okay, now we're going to write the test bench. In a test bench, when you are writing the test bench, start in the same way, that is, start with a module. Give one module name. Suppose I am going to test the full adder underscore TB. Okay. Now, when you are writing test bench, no need to give any input output here, because test bench is a program just to test your design. So test bench does not have any independent input output. So that's why no need to give any input output here. Just open close this one. Okay. Then, whatever the input parameters are there, A, B, C, I, okay, those are the input parameters. So I'm copying it directly here. So inputs are declared as, in the test bench, inputs are declared as register type REG. Okay. Now another one thing, whenever you are writing the test bench, the internal details of this design is not important. You are going to test it. That means you can assume that is a square box, okay, whose input is ABCI, output is SC0. But what is inside that box, that is not important. Okay. So output is S and C0. While writing test bench, you declare the S and C0 as a wire type. S, C0, CO. So always follow this one. The inputs are declared as register type, output is declared as wire type. See here, wire declared for a temporary connection, but here wire means output. So be careful. Then call your main module. The module you want to test, that is this one, full adder. The module name is full adder. You have to give the same module name. We are calling this. Now we are calling the full adder. Okay. Then give one label. Suppose you want any label you can give. Okay. Follow the same sequence. So S, comma CO, comma A, comma B, comma CI. Done. We call this. Now the main module calling done. Then we have to give some standard input. Initial begin. Okay. Followed by end statement. Inside begin and end, we have to give some standard input. Suppose ABCI, so three inputs are there, so we shall put A equal to 0, B equal to 0, CI equal to 0. Okay, hash 20. The hash 20 indicates we are giving one delay of 20 nanoseconds. So why delay is required? So without giving delay, if we change, then if we write the next data A0, B0, CI1, so the data, the change in data will not be reflected. So after putting one test input, you have to give some delay so that the input will change. Okay, the change will be reflected. So just copy the same line, 0, 0, 1, then 0, 1, 0, then 0, 1, 1. Okay, okay, it's not okay, fine. Then 1, 0, 0, then 1, 0, 1, then 1, 1, 0, then last one is 1. Basically, we are putting the truth table 0, 0, 0 to 1, 1, 1. Okay, this one, then you, it's better to write the $finish. Otherwise, your test bench will run for the final time, that is written 10 millisecond. It will run up to 10 millisecond, which is long enough. Okay, otherwise, if you want to terminate it before this, you give a $finish. Okay, so end, finally end your module and module. Okay, so this is the complete test bench feature. Now, okay, just 1 minute. Okay, we came here. So that is done. Now we have to add 2 extra line, that is basically simulator specific comments. Okay, simulator specific comments. That means okay. the line is 2 line you have to add $dump file equal to dump.bcd and $dump has. Okay, so these 2 lines basically it is required to generate the waveform in this platform. So this is not a standard, you can say this is optional for any other Verilog simulator, but it is mandatory in our case. Okay, that means without those lines the simulation will be done, but you will not get any output. Okay. You will not get any output. Okay, then why these things are coming? Okay, so you have to give these 2 lines. So just make sure this tool simulator selected, this one, this one, this one. Okay, fine. Now tick this one, open EP Wave after run. Okay. Otherwise you will not get the output. Let's check once again. This is your design code. This is your test bench. Those are the test inputs you are applying. Okay, now let's run the code. Oh, there is some problems, I think so. Process not found on server. This is some network connection error, I think. Okay, if you got this type of, so generally the signal comes automatically. If you got this type of signals, this type of messages, so get signal. Okay, so your test bench, select your test bench, fa underscore tb. Okay, and append all. Okay, and then you will get the output. Okay, so generally after selecting this, and if you run, automatically the waveform will come. And by chance if it is not coming, then go to get signal. Okay, this one, select your test bench module. Okay, then append all here. Yeah, so this. Now let's check. So let's check here. See, 0 0 0 sum 0 carry 0. 0 0 1. Okay, 0 0 1, definitely sum 1 will be carry will be 0. Then 0 1 0 sum 1 carry 0. Then 0 1 1, so 1 1 and this one, so sum will be 0, carry will be 1. So I'm checking the last stage, 1 1 1 sum 1 carry 1. So you can check this. So the result is coming, that is true. So you can take a snapshot of this one that is required to write your report. Okay, so do not close the full, close this one. So this is the simulation. Okay, another one thing, if I want to visualize, okay, the system which is designed in form of block. Okay, so see how we can do that. Okay, before doing that, see that if your simulation is successful, the dump.bcd file will be generated and this type of messages will come. Okay, now in the second stage, so we are going to synthesize your design. Synthesis means how the system is implemented. Okay, so just change the tool and simulator to this one. EOS is 0.9. Okay, and whatever the synthesis option, no need to change. Stick on that, show diagram after run. Okay, run it. Yeah, see, this is the AND block. Okay, input is AB, output is some Y. Okay, this is another one AND block. Okay, this is another one AND block. Okay, so this AND block, AND block, AND block. See, this is W1, this is W2, this is W2, and this is W3. Ultimately, W1, W2, W3 goes to OR, and C0 is generated. The XOR block, see, the XOR block here internally, two XOR gate is used. Okay, this XOR, two input. Okay, this comes to the third one, sum is generated. You also take a snapshot of this. So this is the synthesis result diagram. Okay, that means how the design has been implemented, means synthesized. What are the internal hardware details? So you can check on the synthesis. So many things can be done by using the commercial softwares, which is actually available in our Verify lab. But in online platform, we cannot do more than that. Okay. So for each part, now, okay, another one thing, the synthesis, for the synthesis part, this test bench is not required. That means you can run synthesis after writing this design code and just set the tool and simulator to this one, show diagram after run, you will get the diagram if your code is correct. But to generate the waveform, okay, you have to select to this one, you have to select this one, run it. Yeah, this time it came. Okay, fine. So this is all about your 1-bit full adder design. You just try from your side. So first time when you are doing it, so maximum cases students facing the syntax error issues, the problem in the module, missing semicolon. Okay, so suppose you start begin, there is no end, there is no end module. Those are the common mistakes. Okay, typing error. And another one important thing, this one. So here you call sum first, carry, then ABCI. So you have to follow the same sequence. Here if you mention C0 first, then sum first, that means C0 will be assigned to sum. So that is basically the function calling, something like function calling. Okay, if you pass the parameter C0 here, here it is sum, then C0 will be assigned to sum here, which is wrong. Okay, so you have to follow the same sequence. Here also you can take a different name. So instead of A, B, C, S, and C0, you can take X, Y, Z, MN, whatever. Here, okay, 5 different name you can take, no issues, but you have to follow the same sequence. Okay, so instead of taking S and C0, if we take X and Y, so here it will be X and Y. Got it? Then the waveform you will get, instead of S and C0, it will be S and Y, X and Y. Okay. So the property is similar to your function calling in any programming languages. So this is for a single bit full adder code. It's synthesis, it's simulation. So for synthesis, you have to go to this synthesis. Yours is 0.9, 0.3, 0.2, you can try, it will work. For simulation, you can go for this one, Aldic Divider Pro. Okay. So today up to this, and in some other class, we shall do the same thing. So this is a gate level modeling. We can write the same thing in data flow modeling. Okay. Okay, let's do now just a one line modification. For data flow modeling, you know that the diagram is not required, only Boolean expression is required. So what changes I am doing? So here assign keyword will be used. Assign A is equal to A XOR B XOR Ci. The meaning of this line, there is a is, that is basically XOR operation of A, B, Ci. So this is XOR operator in your keyboard. You can check. Okay, bitwise operator. Okay. Similarly, assign CO equal to, that is A and B. This is OR operator. Generally, it is found below backspace. Okay. Then B and Ci, B and Ci, OR operator. A and sorry, A and Ci, semicolon. So give one space here. Okay, so assign CO equal to this. So if you know the Boolean expression, so directly things can be done. Now let's first simulate it. Oh, some problem is there. Yeah. So many signals are coming. Okay. Two times the signals are repeated, no issues. So you can just check it. The output is same. You can check whatever the output you got in the gate level modeling, data flow modeling, the same output will be there. So only change will be here. So there will be no change in the test bench, because in the test bench, what internally we are doing, that is not important. Okay. What internally we are doing, that is not important. Okay. So this architecture part, that is not important. In test bench, we are only dealing with the input output port. That is already mentioned here. Now let's do the synthesis and let's see how the diagram will come. Yeah. Let's do it again. Oh, so diagram after that, sorry. Yeah, basically it is same type of diagram. Okay. Now whenever you are changing the architecture, the diagram may change a little bit. Okay, because the synthesis depends upon the modeling methodology you are using. Okay. So that's all for gate level and data flow modeling. Now see, in the data flow modeling, the code is much more simple. We are not calling any logic gate. We are using a direct operation followed by assign keyword. But you need to know what is the relation, Boolean function, relation between input and output for data flow modeling. Okay, so that's all for today. In the next class, we shall discuss how to design a 4-bit full adder to design a single bit adder. So take a backup of this code and this code in a text editor, notepad or something. Okay, and store it separately. One is design code, another one is test bench code. Okay, so that's all.